Yeah, I always end up closing that because when I'm here, like from 3 to 6 for physics, it's just like sun right in your eyes. I'm sitting right there.
Yeah, it's
So that's why I keep closing.
It's nice in the morning though.
yeah, you gotta make it work for you, right?
Totally.
All right, let's take a look at the quiz. Although everybody in here did pretty well on the quiz. But Cody, did something change? I don't remember seeing your name when I was grading yesterday. Did I just fly through it?
I don't do that.
Okay. That's totally fine. You're just auditing. I was just, usually I see your name, and then it was occurring to me this morning that I didn't. All right, so naming, relatively straightforward as far as how some of the things we're doing these days, right? Naming is sort of our safety blanket at this point. There's some wrinkles, but you can always get close. So in this case, with longest continuous chain with the alkene, just goes left to right, which I believe makes it I think it's heptene. And so you could say hept2-ene or 3. I can't count. So we're starting counting from here, 1, 2, 3. We're going to keep that number as low as possible. Then we just name branches, and this one's got 4 methyl groups attached to it, so it's going to be tetramethyl, even though they're attached to different carbons. So, and I think everybody got that. And the biggest confusion was, and so then naming, we have to say where all of them are, so it'd be 3, 4, 5, 5. Tetramethyl, remember you need, if it's tetra, that means 4, means you need 4 numbers. And then the last piece is we have to say whether it's E or Z. If you have 2 different things attached to each end of the alkene, then we have 2 possible stereoisomers. And so we specify which stereoisomer we have. And I'm going to just erase this and recircle it. So attached to the red carbon, we have carbon and carbon, so ties, so you go 1 step out. Carbon, the next step out from here would be a hydrogen. So higher priority is here, lower priority there. And then for the carbon circled in black, we have a methyl and an ethyl. So the ethyl is the higher priority, methyl is lower priority. So our 1 and our 1 are on opposite sides. So you could name this, because the primary carbon chain is on opposite sides, you could name this as trans, but the better naming system is that E and Z. And so with our higher priority being on opposite sides, that's entgegen, or E. All right, and that process, if you can do R and S, E and Z is the same, but it's even easier because you don't even have to think in 3D, right? So it's pretty straightforward. You just have to remember to check it. And you're going to have to do E or Z anytime you have 2 distinct substituents on each of these. As soon as one of these 2 carbons has the same thing on both sides, then you can't assign priority, right? Which also means if you flip them, there would be no difference, in which case there is no E or Z. If both of these were methyls, there would be no E or Z, because switching them is the exact same molecule. If both of them were ethyls, if both of them were hydrogens, it doesn't matter what it is, if they're identical, then you don't have to specify E or Z. There is no stereoisomer in that case. This one didn't have an E or a Z, and I didn't explicitly state this, so I've made it a bit of a trick question on accident, that ring structures are always assumed to be Z. They're always assumed to be cis on the same side, because otherwise the ring structure winds up being really, really strained. Turns out you can do it, but it's not very common. You have to have a really big ring structure If you picture a cyclooctane, you could, in theory, have 1, 2, 3. Something that looked like this, where you had the cis or the trans structure, but as you see, it would have to be forced sort of out of being planar. It wouldn't be a very stable structure. There'd be a lot of strain energy on it. So we assume every ring structure is going to be E or Z, excuse me, unless otherwise specified. So you didn't have to specify E or Z, but you did have a stereocenter still. You still had R versus S. So you just had to assign the priority to do that one. And see if I'm remembering right. So highest priority, 2, 3, and then the hydrogen coming out is 4. So that would be counterclockwise, except we're looking at the back of the clock. So clockwise, so R. I'm starting to think that for R and S, it's almost easier to move your point of view rather than redrawing the molecule. Redrawing the molecule is usually the way it's taught, but the more I teach this, the more it seems easiest to just move. You could physically move your piece of paper on a test if you're trying to do this, rather than trying to redraw the molecule. Whatever works for you, but if you like just moving your point of view, stepping through the paper as it is, or putting your face in line with the paper and visualizing out of the paper and behind the paper, whatever works for you, that's a perfectly valid way of visualizing these things, and maybe is perhaps less prone to dumb mistakes because you're not redrawing anything. Right, so anytime you redraw something, that's a potential spot for you to make a dumb mistake. So keep that in mind, I guess. This one I wanted to use as an example of basically when cis and trans is not the same as E and Z. Cis and trans refers to the primary carbon chain. So the primary carbon chain here goes like that, so it would be cis. But the higher priority does not follow the main carbon chain in this case, the current molecule. So the higher priority would be 1 and 1. So for higher priority, it would be E, but if we're naming it with cis and trans nomenclature, it would be cis. So this is, again, why we can't just use E and Z and cis and trans interchangeably, because most cases, they're going to be tied to each other, but you can have cases like this where the carbon chain, the main molecule, is not the highest priority. Right? So best to you still understand what cis and trans are, because we use them to describe relative positions of things, especially with rings. But for naming things, E and Z is a much more robust and uniform system. All right, an E2 reaction. So R, 3-bromo, 2,3-dimethyl pentane. So again, when you're trying to, if you're starting from a specific stereoisomer and you want to draw it, just pick one way to draw it and then check to see if you drew R versus S. If you can start from a structure and identify R versus S pretty reliably, then you don't need to draw the right isomer the first time. Just draw an isomer and go check which one you got. So start with pentane and draw it whichever way is convenient. 3-bromo, 2,3-dimethyl. So this is the molecule we're working with. If I'm going to check which of these has the highest priority, bromine's the highest priority, then the isopropyl group, then the ethyl, and the methyl is 4. So 4 is already into the board. So just by sheer luck, I happened to draw R the first time. Nice thing about it, that's a 50-50 shot, right? So half the time, you start with the right isomer. All right, so if it's treated with water, and water is also the solvent, sorry, I switched problems. It goes through an E2 reaction, so simultaneous elimination, forming 4 different alkenes. So our leaving group is going to be the bromine. That means anything adjacent that has a hydrogen that can leave could form the pi bond with the carbon that has the bromine. Had the bromine. Right, so since all 3 of the beta carbons have, alpha carbons, all 3 of the alpha carbons have a hydrogen attached to them, we could make a pi bond in any of these 3 directions, and if there's any that give us stereoisomers, that's a possible product as well. Right, so if we make a stereoisomer, if we take a hydrogen off of this carbon. So we're going to remove that hydrogen, remove the bromine. All the carbons stay more or less where they are, except now we have a planar carbon instead of, so we lose the stereochemistry here. So that's one possible product. I'm actually going to redraw it a little bit smaller so I can fit everything here. Do we need to worry about system trans for that one? No. Why not? Those 2 methyls are identical, right? So it doesn't matter which one is where, because if we switch them, we get the exact same molecule. So if we, instead of taking off that hydrogen, if we remove the hydrogen from the methyl group, same carbon structure, make our pi bond to the bottom carbon, E and Z, 2 hydrogens, right? So still no stereoisomers here. The last spot that we could take off a hydrogen would be right here. And that would give us that molecule. Now we have E and Z, right? Because you have hydrogen and the methyl, and on this side you've got an isopropyl and the methyl. So you can tell the difference between the 2 things attached to each side. So then the last one would be the Z version. And the last thing that we covered before we ended class the other day, which was now in a bit, right, was Zaitsev's rule. And Zaitsev's rule is that under normal circumstances, you favor making the more substituted alkene. Right, so our highest likelihood would be the alkene that's tetra-substituted, or that has 4 carbons attached to it. And these both are tri-substituted, so they're going to be roughly the same amount. We'll talk about how we could actually split hairs and determine which of those is slightly more likely today, because we can look at the shape of the transition state is actually going to allow us to predict which of them is going to be more stable. It comes down to Newman projections, basically. In other words, sterics. So just at first glance, we can say, well, we've got a big isopropyl group here pointing in roughly the same direction as a methyl group. It's probably going to be more favorable to make this product, because that puts the biggest group, physically largest group, from each carbon pointed in opposite directions. But they're going to be in roughly the same amounts compared to these others, and our least common product is going to be the terminal alkene, the one that only has 2 substitutions. Yeah, we'll leave that for now. And the last one was a SN1 reaction. And we knew that because there's a couple of key clues here. It's treated with water. So water is both the nucleophile and the solvent. So we've got a polar protic solvent and a weak nucleophile. And a really good leaving group. So all of those things point towards it's going to be a stepwise mechanism. So we can expect to make an intermediate that looks like a carbocation, right? First step in these stepwise mechanisms is leaving group leaves. So our intermediate then looks like this. So now we have a nucleophile in the form of water that could come in and attach, and then it would go through a proton transfer where it's going to dump off its extra hydrogen. So we're going to wind up with an OH group, an alcohol group by the ends. But first we just want to say, okay, well, we can either have, remember that the carbocation is totally flat and planar. Right? When you have a leaving group leave, a carbon with only 3 bonds with an incomplete valence doesn't have a full sp3 hybridization because it has an unoccupied orbital, an unoccupied piece of the p orbital that's not mixed in. So you get sp2 hybridization, which means it's going to be trigonal planar. This charge basically goes equal amounts up and down from the carbon. So our OH, or our oxygen, can come in and attach either from behind the board or in front of the board to get 2 different stereoisomers. And so if it attacked from behind the board, we would get a product that looks like this. If it attached from in front of the board, we get the product, the OH, sticking out towards us. And most of you were able to get that, even if you're still struggling with why it's a 50-50 mixture. It's 50-50 mixture just because that p orbital is the same shape above and below the carbocation. So that means you've got an equal chance of the oxygen hitting it from the top or the bottom. That bromine's totally gone, it's not taking up space anymore, therefore you have plenty of space from behind or in front to attach. What most of you struggled with, or didn't catch, is that this can't go through a rearrangement, but it can go through resonance. There's a resonance structure here, right? Resonance structure would be, okay, well, if I have an empty p orbital over here, switch colors. Those pi electrons can move over, and we wind up making a different resonance structure. Is that too many? No, that's right. It looks like this. And so then in this case, now we have a different carbocation that the hydroxide could attach to, that the oxygen could attach to. And this one is not going to have R versus S, right? Because two identical methyls attached. It's not going to have four unique things attached to it. So in this case, the OH could attach from either side, just as before. It could attack from behind, from underneath, or it can attack from on top. But in both cases, you're going to wind up with the same molecule because these two methyls are identical. So it's no R versus S. But this resonance structure could be either, we do have E versus Z. When this resonance structure happened, it sort of locked these carbons into the same configuration, right? But they could have been in either configuration when it switched over, right? So you were just as likely to get a resonance structure that looks like, and I'm going to have to start, so that I leave myself enough room here, I've got to start from that's just as likely as the resonance structure, right? Because those, when that leaving group leaves, whatever configuration it's in when the leaving group leaves is where it's going to stay. So both of these are possible. And again, due to sterics, we might expect this one to be slightly more likely. But that means that we get, let's see if I can do this without running into anything else. Nope. Get this molecule as well. So total of 4 products again. And this is basically the rest of this class, and when it comes to mechanisms and reactions, is going to be these same 4 mechanisms we're dealing with, because we're getting into them in pretty good detail, right? And a big chunk of the final is going to be draw all possible products if it goes through this mechanism. Draw all possible products if it goes through that mechanism. And so it comes down to sort of understanding we have these 4 options that are really, it's not, you know, every molecule that goes through this reaction is going to have to choose one of those 4 pathways, but it's not like we can really get it to a point where only one of these happens. We get to a point where one of those 4 mechanisms is favored very strongly, maybe 1,000 to 1 over everything else, but we can never totally eliminate the other mechanisms. They're always going to be a path that they can go through, even if it's highly unlikely due to the energies. Right, so again, it comes back to my favorite description of chemistry from Interstellar. Everything that can happen does happen. These things can happen, it might just be unlikely or happen less frequently than some of the other choices. Right, so that's why you never get 100% yield of one product. There's always something else in the way, or the reaction doesn't go to completion because of equilibrium constants, or some side reaction that you didn't even predict happening. Right, so if you're feeling like that was a really tricky one, it's because it is, and we're going to keep spending time working on these until you get a little bit more comfortable before we add more mechanisms, which won't happen until winter quarter.
Is there a possibility that this also undergoes an SN2?
So there'll be some amount of SN2. But the fact that water is such a weak nucleophile, and that we have a polar protic solvent, which favors stabilizing the intermediate for SM1. SM1 is to be the favored mechanism, but yeah, the nice thing about SN2 is your SN2 product is pretty much always going to be the same as one of your SN1 products. If it goes SN2, you only get one possible product though. If this went through SN2, we would only get the isomer that looked like this. Because there is, while the resonance can stabilize the transition state a little bit, it can't actually resonate to the point of putting a positive charge here because your nucleophile is coming in at the same time the bromine's leaving, so it has to be on the same carbon the bromine's leaving from. So in a lot of ways, this concerted mechanisms, the transition states can look more complicated because you've got more things happening at the same time, but it also means that you have fewer possible products, so they're actually usually simpler because everything happens at once. We'll see the same thing with E2. Second order elimination reactions are the same thing. Because everything has to happen at the same time, there's no chance for rearrangements or resonance to really play a role. A mess. There it is. All right. I don't want to mess with somebody keeps moving the position of the screen back, so I don't want to play around with that. So we'll just do this. I'll just use one more on the side. When doing reactions in the lab, how can we observe whether something's concerted or stepwise? Usually the best way to do it is with those method of initial rates. Do the same reaction twice, but double the concentration of the reactants, of one of the reactants, and see if you get the same rate or if your rate doubled. Then if you do the same reaction again, so you double the concentration of the other reactants, and then you observe whether that changes or not. Because remember, all of these, if it's a second order reaction, meaning concerted reactions are second order, which is where the 2 comes from. It's always going to be the rate constant, and the order of the reaction has no effect on the rate constant. Times concentration of reactant A times concentration of reactant B. So both of these concentrations affect your overall rate. If it's first order, only one of those does. If it's first order, if it's stepwise, then the concentration of your nucleophile doesn't matter. So I can actually get more specific here. Instead of using A and B, we can say that it's R, say it's a bromide we're dealing with, and nucleophile. If it's second order, then both of these concentrations affect it. If it's first order, the slowest step is leaving group leaves before your nucleophile can come in. So the nucleophile concentration has no effect on your overall rate. So in this very specific case, where we already know that if we know it's very specifically one of these 2 options, we don't even really need to do the experiment where we vary the concentration of the organic molecule, because we know that that's going to play a role. Unless something really weird is going on, at least beyond what you guys have seen so far, we really only need to test the nucleophile concentration. Sometimes there are cases where the concentration of your carbon-based molecule will affect the rate. You can have things happen where maybe generating the nucleophile is your rate determining step. You have to make your nucleophile by, I don't know, splitting ozone or something like that, and that's your slowest step. It all comes down to what's present in your slowest step of these multi-step mechanisms. So in this case, though, we're not dealing with any of that. Our slowest step is leaving group leaves, or it's inserted, and it's only one step anyway. So somebody else asked about the concept of how strong of a base something is tied to its how good of a nucleophile, or why is a strong base an unstable base. It has to do with the fact that if it's a strong base, it's a good base, that means it's really, really good at pulling protons towards itself. And that's going to happen most frequently with things that they're good at pulling protons towards themselves because they're unstable the way they are. They get more stable when you protonate them. So if you have something where, let's just use hydroxide as an example. Hydroxide's in a situation where it's got a potential energy surface that looks like this. And let's say we've got just H plus attached to something else. So we'll call it HA for acid. We're making the deprotonated form of the acid and the protonated form of our base. If it's downhill in energy for the hydroxide to steal a proton, then this is the more stable state. This is what's more likely at equilibrium, right? So in other words, an unstable base is a stronger base, is a better base by virtue of being unstable. The more unstable something is, the faster it's going to find a way to make itself stable by reacting with something else. So for reaction to be spontaneous, this always has to be downhill. But the degree of downhill is what's going to determine how strong of a base something is. All right, and so we usually compare these. The reason we always use pKa's to evaluate how strong a base is or how strong of an acid is we're comparing it to water always. So instead of HA, if we said, I think this is a bad example, let's switch the hydroxide into being amide, NH2 with the negative. We always compare everything to water because water is such a common solvent and it's always around. So if something is a strong base, it's better at pulling a hydrogen away from water than hydroxide is at pulling a hydrogen away from whatever the conjugate base is. So, the conjugate acid. So amide, if it steals an H plus, turns into NH3. Water, when it loses an H plus, turns into hydroxide. Turns out this is much farther downhill in energy than this. Therefore, we would say that amide is a stronger base than hydroxide, because at equilibrium will favor this state, not that one. And typically, if something is really unstable as a base, it's also a good nucleophile, because it's really good at pulling hydrogens off of stuff, but it's also going to seek out any partial positive. Hydrogen ions are really convenient partial positive because they transfer really easily in an acid-base reaction, easily, quickly, they're everywhere. You have a protic solvent. But any partial positive, like the carbon that's attached to a halogen, is going to be a target. So, and if it's unstable this way, it's also unstable in terms of it'll make a bond with a carbon as well. Right? So strong bases, unstable bases are strong bases and generally also strong nucleophiles, unless we have that protic solvent happening. A polar protic solvent can change that slightly because of the stabilization of water molecules surrounding your nucleophile. All right, and then we already talked about this a little bit, but I found a figure that I don't think I threw this figure in this year's slides, but that's from a textbook I used to use. This figure is actually explaining why more substituted carbocations are more stable. In this case, we're talking about if you have a carbocation it's going to have, that's the carbocation is the purple orbitals here, and it's that unhybridized p orbital that's going to stick it straight up and straight down. And if you happen to have other tetrahedral carbons around it, then they can't really give electrons to it very easily, but they can give a little bit, they can help out a little bit. You know, this is, they can't give all the electrons because they need the electrons for itself, but they can do, it's like giving $1 to somebody who needs $50 to buy a bus ticket. It's not helping much, but it's better than nothing. Right? And the more people you have around that can do that, the more likely that is to be stabilized to buy that bus ticket. Right? So more substituted carbocations are more stable for this reason. And if this was a carbon that had a pi bond, then you actually can have direct overlap. And that's what resonance is. It's similar. This is what's called, this is referred to as hyperconjugation, because it's not truly conjugated, because you don't have a pi bond, but it's like conjugation in that it's giving a little bit of electron density. And it's the same way that rearrangements can happen too. Because if this is the carbon that's more stable with a partial positive than that one, then it will give enough of its money. And now all of a sudden we have something over here that's got a vacancy, but if it's more stabilized because it has extra carbons around it, if we made a tertiary carbocation from a secondary carbocation, the mechanism is just what this looks like. You just basically, this electrons, pair of electrons just slides over into the empty p orbital next door. And you're left with an empty p orbital on this carbon now. But if that happens to be more stable than what you started with, that can still be downhill in energy. All right. Let's do a brief recap of elimination reactions. And we'll talk a little bit about stereochemistry with elimination reactions. Excuse me. So just like with substitution reactions, elimination reactions had two possibilities. So substitution was your nucleophile comes in and makes a new bond with the carbon, and your leaving group leaves, typically in the opposite order or at the same time. In this case, instead of a nucleophile, it could still be a nucleophile, but we're going to call it a base because it's acting as a base. Maybe it's just because I've been saying the word base this whole time, but it's a little bit like if you've got a multi-instrumentalist playing in a band. They're playing bass in the band, they're the bass player, right? Whether they also play piano or not. They're filling one role, regardless of what else they can do. So despite the fact the base is probably also a nucleophile, in this case, we're just going to refer to it as a base. Maybe it's just because I've been seeing all the pictures of Paul McCartney from that Beatles documentary. Anybody watch that yet? I'm not a huge Beatles fan, but anything that's well done with good, that talks about music making process and songwriting, I'm a sucker for it. I'll probably wind up watching with my in-laws because they love the Beatles. All right, so in this case, if it's concerted, our base is stealing a hydrogen from the alpha carbon. Remember, carbon 1 removed from the active carbon. And I guess we should get really specific with that. So the alpha carbon is 1 carbon away from where your leaving group is attached. Beta carbon would be 1 carbon further away from that. This is not the alpha carbon, because this is the active carbon. Right, so it gets a little bit hazy when you're defining these. The way I always have to remember it, because I was tested earlier today to call the leaving group the alpha carbon, is that with carbonyl carbons, this is the alpha carbon, and this is just the carbonyl carbon. And then the naming keeps going, and then you have a beta, a gamma carbon, although typically we don't really care about anything that's further away than 2 or 3 carbons from our active carbon. For naming things, we do. So actually, where the name for GABA, the neurotransmitter GABA, stands for gamma aminobutyric acid. It's an amino acid, but instead of being an alpha acid, where your amine group is attached to the alpha carbon, from the acid group is attached to the gamma carbon. So our base if it's concerted, our base has to be taking a hydrogen away from the alpha carbon at the same time as our leaving group is leaving, and the electrons that were in the carbon-hydrogen bond are going to move over to make the new pi bond. Right, so your leaving group is leaving and it's taking its electrons with it, and that's leaving a vacancy, which is going to pull the electrons from the carbon-hydrogen bond over into a pi bond, while the base is grabbing the proton. Yeah, sorry. All right, so drawing your arrows can get a little tricky for this. Even if you know that the base has to come in and attach, it can be easiest to start by drawing leaving group, leaving arrow. And then think about, okay, now where is that going to pull electrons from nearby? Because it has to have a carbon-hydrogen bond on an alpha carbon, on an adjacent carbon, in order to do this. And if it's stepwise, leaving group leaves, just like before, that's the only thing that happens. Still a total of 3 arrows, mechanism arrows. They're just split up now. All right, so when we talked about regioselective, we talked about how we're preferentially going to form the more substituted carbon, so I'm going to go fast through this. And when all of the beta carbons are identical, you're only going to make one possible product no matter what. I guess I can't say no matter what, because there's a possibility you still might have to worry about E and Z, despite having identical beta carbons, or sorry, alpha carbons. I got confused in my own slide here. All right. We didn't update. We just didn't say it. There we go. When the alpha carbons are different, you get the combination of products, and we're predominantly looking at how many substitutions there are. We're following Zaitsev's rule. And Zaitsev is interesting. We'll learn about Markovnikov's rule when we talk about addition reactions, which are basically the exact opposite of an elimination reaction. An elimination reaction, a leaving group leaves and you make an alkene. An addition reaction, an alkene is attacked by an nucleophile, and you wind up basically undoing an elimination reaction. And so Markovnikov's rule talks about which isomers are formed when you do an addition reaction. And Markovnikov and Zaitsev were in the same research group in Russia in the late 1800s, early 1900s. And they were, I want to say Zaitsev was the younger student, but he was always picked on by Markovnikov. Markovnikov was known as not being a particularly pleasant person. Something about Russian organic chemists that kind of get that reputation, I guess. So Markovnikov published part one of a 3-part series on elimination and addition reactions, and it was seminal work. Found it, he still has a name, a rule named after him, Markovnikov rule, to this day. And then Zaitsev noticed that there was an error in part 2 and didn't say anything, and let it get published incorrectly, and then immediately published. He had his paper ready to go right behind Markovnikov's paper, and sent it in to basically get Markovnikov's second part of his 3-part series thrown out. And that's where Zaitsev's rule comes from. It's from the work that he did that shows, oh, that Markovnikov guy really doesn't know what he's talking about. There's something about, I think Markovnikov kept Zaitsev from getting his PhD for an extra 2 years or something like that. He was on part of his review panel or something like that, and he basically failed him for no good reason other than pettiness. And so as Zaitsev was not particularly pleased with that. And he said something really nasty, like there's something in print about how he's a worthless chemist and nothing he does will ever be any good or something. Like it's really vicious. And maybe part of that's the translation, but still. All right, let's go through these. Actually, I'm gonna leave these for now. Come back to them after break. Let's talk about exceptions to Zaitsev's rule. Because you guys worked with that a little bit over break already on that quiz. There was a German chemist named Hoffman who basically figured out how to get the opposite to be true. The Hoffman product is the less substituted product. And it's called the Hoffman product because Hoffman figured out that if you make your base big enough, physically, sterically large enough, it actually can't get to the more substituted carbons. So instead of making the more substituted alkene, if you use a sterically hindered base, you get the least substituted product. So, and the most common sterically hindered bases are listed up here. You can see why they're considered sterically hindered. Tert butoxide, so a T-butyl group or a dimethyl ethyl group attached to an oxygen. This big carbon group just physically prevents it from getting as close to the more substituted carbons. There's just not enough space for it. And as a result, you get the Hoffman product. The abbreviation we use for this is TBUOK, which is contrary to the way it should be written if we're following normal ionic nomenclature. Normally we put the positive ion first, but since we really don't care about the potassium ion, it's really only there to balance the charge. It gets written like this in organic chemistry books. So this is probably the most common of these that we see. If you see this, that should just be a trigger. Oh, not Zaitsev's rule, Hoffman. We're going the opposite direction, sterically hindered base. Some others are diisopropyl amine and triethylamine. And for the same reason, in both these cases, you can see the group that's actually going to be accepting the proton is surrounded by these big bulky R groups. And so for the same molecule, if we have it going through a normal elimination reaction, we make the Zaitsev product and the Hoffman product. If it's a normal base, like ethoxide or hydroxide, you make the Zaitsev product much more commonly, 71% to 29%. As soon as you make it TBUOK, those flip almost exactly. And if you make it a more sterically hindered base, if you take it and make it even larger R groups, then you can skew that percentage further in favor of the Hoffman product. Right, so I'm not going to ask you to come up with percentages off the top of your head or even estimate them on a test especially. You just want to know that if it's sterically hindered, the major product flips. We go towards the least substituted product winds up being our favored product. And these reactions are also, so they're regioselective, meaning that you're favoring putting that pi bond in a certain place. But then even within each of the pi bonds, this is what I was hinting at earlier, you can wind up with two, in this case, you have two identical alpha carbons, right? If you have two identical alpha carbons, you can't have a different alkene, other than you can get E versus Z. So in this case, this is what's known as, what they're referring to as stereoselective, means in addition to choosing where to put the pi bonds, it's going to follow these predictable rules, which stereoisomer you get is also going to depend on some of these rules. So in this case, we get the trans product, the E product is the major product. And the minor product would be the Z, or the cis isomer. And we can predict that by looking at what the Newman projection looks like for this molecule. If we look down this bond, so if we're looking from up here, looking down that way, on carbon 3, we're going to have a bromine, and, bromine would be sticking in one direction or the other. And then that would be an ethyl group, and then a hydrogen here, and then the front carbon has a methyl pointed straight down, and then two hydrogens. If this is going to go through an E2, a concerted elimination reaction where your bromine has to be leaving at the same time as one of these hydrogens is being pulled off. In order for all of those orbitals to line up in the right way, this carbon-hydrogen bond has to be pointed in the same direction as the pi bond is going to be, in order for those orbitals to overlap enough, which means it also has to line up with the anti-bonding orbital for the bromide. And basically what that means is that your leaving group has to be coplanar to the hydrogen that's leaving. Your hydrogen that's being pulled off and your bromine have to be in the same plane. They have to be flat. Otherwise, you can't get the orbitals overlapping the right way, and you can't get the new bonds forming and the old bonds breaking the right way. So that means knowing what your Newman projection looks like can determine which E versus Z is going to be more preferential to form. And it's going to be based on sterics. If we had to choose where to put this bromine in order to make it, it has to be opposite of one of these two hydrogens. Does it really matter where the bromine is if it has to be opposite of these two hydrogens? Bromine's going to have the same interaction with the methyl either way, right? But if we move the bromine over here, then all of a sudden, and let's leave the front alone. So if we move it coplanar to this hydrogen, we added an interaction between the ethyl and the methyl, right? The ethyl and the methyl were opposite from each other, and now they're gauche. They're right next to each other. So we would expect this to be less stable than this. And if you take away this hydrogen and the bromine and everything flattens out, that puts the ethyl and the methyl facing opposite directions, right? So it's sterics that determine which of these we get, which of these is favored. The one that's going to put the two largest groups opposite from each other is minimizing those Gauss interactions while still keeping a bromine opposite of a hydrogen. Right, we can't put the bromine up at the top because then it wouldn't be opposite of a hydrogen. We can't have the elimination reaction happening there. So our two choices, the net result is that generally we can just look at these and say, okay, well, whatever the two biggest groups are have to be opposite of each other. You're going to favor making the E, or the trans conformer, or stereoisomer. But it's because they have to be flat. And the reason I'm stressing that instead of just teaching you the generalization is there are some times where you only have one possibility. If your alpha carbon only has one hydrogen to lose, then your bromine has to be opposite of that hydrogen for the elimination to happen, regardless of what else that does as far as sterics. Right, so for instance, in this case, if we have bromine, I guess this is the old textbook I was using, had the alpha carbons listed as the active carbon, which is why my slides did that. I still don't like that though, because alpha carbons are next to a carbonyl, not the carbonyl carbon. So I'm going to continue using the way we defined it earlier. Ignore that on this slide. So if you look at the alpha carbons, the carbons that are next to the carbon with the bromine, the active carbon, that alpha carbon doesn't have any hydrogens it can lose. It's a quaternary carbon that already has 4 carbon-carbon bonds. We're not going to break one of those. This alpha carbon has only 1 hydrogen. So in order for the elimination to happen, the bromine and this hydrogen have to be opposite of each other. So you don't get a mixture of this cis and trans in this case. You only get one possibility. Because the hydrogen and the bromine have to be coplanar. And just to, where's that definition? Mathematicians get upset with chemists when we make generalizations like it has to be coplanar. Technically, they don't have to be exactly coplanar. They have to be close to coplanar. They have to be closer to exactly opposite than 60 degrees off. But that's not technically coplanar, so they actually came up with another term that, as I understand it, is we only use as a result of mathematicians getting angry at chemists for using coplanar when they're not truly coplanar. So if it's coplanar within sig phase, then they call it periplanar, which means about coplanar, close enough to coplanar. But because we're not using the word coplanar, the mathematicians allow us to do that without being a, well, actually, person. Let's be real, mathematicians are always that person, but if we use periplanar, they don't have a leg to stand on. All right, let's take a break and then we'll practice with these, and then we're going to talk about some lab stuff. All right, so let's come back at 10 after. Did you see that in an email from Ali yesterday about Bio 103's lab?
No, what is that?
Just that, so Bio 101's lab is Monday, right?
No,
It's not?
no, Bio 110 is Monday and Wednesday. Oh, Bio 110 is Monday. So Bio 101 is Thursday and Fridays this quarter.
Thursday and Friday,
Yeah.
right? So they have the option?
Yeah.
Okay. So,
I doubt it'll be like that in the winter.
so it's not, so 103 is only, they're only offering one lab
Oh, that's
session,
really
but it's
cool.
the one that's on Thursday that overlaps with Gen Chem lecture.
Shit.
And since everybody in Bio 103 is probably also in Gen Chem too,
Yeah.
I think that they're gonna want you to move that.
So Friday?
To either Friday or Monday, or just later in the day.
It's not, it's not gonna happen Monday. I
Okay,
think I have zoology.
yeah,
Well, I think my lab's on zoology on Monday, which means I already have 5 hours. So
Right,
I
right.
can do that.
Yeah, I'm just letting, like,
Thank you.
check that email.
Yeah, yeah, yeah.
It's got, so I think what happened is that last year we did that,
Yeah?
and it was okay because we just scheduled conflict waivers because everybody was reporting everything.
Oh, right.
And
Okay.
so, and then this year when they set the schedule, somebody didn't catch that.
Right.
And so I got Antonio Marquez came yesterday, like, I need a conflict waiver for 2-hour overlap,
Oh, wow.
like, for the entire lecture.
No.
We need to fix that, because that shouldn't be the way it is.
Yeah. My email's funky, like, I do
Okay.
not get things for a day or two off.
Okay,
Like, I just got now something that came, I was in my office at 5:30, Kelsey sent me something at 4 o'clock, and I never got it till today.
Yeah.
And it showed up like, I'm like, whatever,
Yeah.
it's so annoying.
yeah, but yeah,
Did she send that today?
I was yesterday afternoon, she and I talked about it.
Okay, cool, let me check it.
Yeah.
All right, yeah,
Yeah.
I mean, that's not your issue, somebody, that's gonna be a
Is it-
huge issue, because we don't have somebody to teach it, and I'm already maxed with stuff.
Right, and so the nice thing about that is though that we don't have somebody scheduled working around now, so we can move it and then find somebody to fill it, as opposed to somebody
Oh, yeah.
having already set up their schedule to do it on Thursdays.
Okay.
But yeah, either later in the day on Thursday, anytime after 3, or Monday, Wednesday, Friday, anytime. It doesn't conflict with me then.
Okay.
So just,
Okay,
and if I'm around, I'm busy, I'm teaching all day today, but if we need to sit down, all 3 of us, to hash
Don't
that
worry,
out,
we'll
let me
figure it
know.
out. I mean,
Okay.
it has to be figured out. We
Yeah. Gotta do it.
because I can't sign that conflict waiver either.
Right,
You know, which
right.
means somebody's got to figure, we have to add a section somewhere.
Yeah,
So
exactly.
it's gonna mean probably is finding out, yeah, we need one more person, or, yeah, I could agree to do it, but,
You're not obligated to.
Yeah, I'm not
You want to.
obligated. Yeah, so the problem is if I do it, it'll be for adjunct wages also.
Right.
I'll do it, but you
It's one of the few, at least you still get overtime essentially, but it's one of the few jobs where when you work overtime, your pay rate goes down.
Yeah.
All right, see you soon. Thank you.
Mechanically inclined to do it.
Oh, yeah, I like
So it's
that.
really like, she rebuilt the engine and I handed her tools and got her.
Well, that's great, man. Some teamwork.
And then she also built a lap bench.
Nice.
I call it a lap bench, we use it as that, but it was for her to rebuild the engine on.
That's cool.
You know.
And also just as a heads up to, since I think most of the people might be interested in this, are in this room, all the stuff that we're not keeping out of the Gen Chem lab, if it's something that is, I think that the cutoff is if you would fix it instead of buying it, or pay to have it fixed instead of buying a new one, is our cutoff for where we have to surplus it instead of just throwing it away. And so there's a fair bit of stuff from the chem and physics lab that is being surplused in the next month or so as we're moving to our tiny lab, and we're purging. A lot of it's stuff, it's not necessarily broken, it's just stuff we don't use anymore. For instance, that rolling lab cart is gonna get surplused, and the way that they surplus it, it just means that they have to basically take it off our inventory for the school. But it also means it can't just be thrown away, it has to go to a government surplus auction site first. And so you guys actually could buy any of that stuff. I wanna say, let's see if I can remember which one it is, there's a few of them. And basically you will only be competing against people that are local because there's no shipping. You can't pay to have it shipped. You have to be able to pick it up yourself or have someone pick it up for you. And so almost nobody wants to come up here to do that. And so you get things like a police cruiser from Libertyville, Illinois. That's current bid is $12,000. That's actually not bad for a 2015 police cruiser. If you don't mind driving there to do that.
Nobody's driving the speed limit because nobody will speed in front of you.
Yes, exactly. I kind of want to see if there's anything. It looks like we don't have anything up here yet. But this is where it will be listed. Anything that we do wind up putting there. Yeah. Hey, Ford. Hey, that's actually not that bad. I'm kind of interested in that. But anyway, so if you keep an eye, I think that this is the one, if I'm remembering right, there's a couple government surplus sites. I think this is the one that LTCC uses, or at least used to use.
Yeah, I don't think it's shared. I'm not quite sure which site you're talking about.
Oh, sorry, I'm on the wrong screen. Like I said, there's a few of them. And you can just go by location. You do one of these and plug in our zip code. You get, El Dorado County has one item listed, Folsom has one item listed. I don't even know what a custom built automatic filter crusher is. Sounds interesting.
It's like a good rock powderizer.
Yeah, exactly. It's custom. Yeah, it does. It looks like a log splitter, except. So, and this one has no bids currently. So if you wanted a rock crusher, there you go. So anyway, just if there's anything in particular, like I don't think I have room for it, but I'm kind of tempted to buy that little reaction cart if nobody else is going to, just because it makes a good work table in a garage. It's on wheels, has a nice table, has a sink built in, although you have to find a way to drain the sink. But yeah, that little one in the back corner over there. Yeah. So anyway, keep an eye on that if you're interested in anything. I just want to see what we're doing. I'll double check. Let's talk to who's in charge of. I think I know who's in charge of surplusing stuff and see.